Welcome to this specialized module on information systems operations. Today we are focusing on the critical connective tissue of the modern enterprise, system interfaces. Systems rarely operate in isolation. They must talk to each other. Whether it is a real-time API call or a nightly batch file transfer, the integrity and security of these interfaces are paramount for operational stability and data accuracy. Let's begin. We start by defining our scope. A system interface is the bridge that allows data to travel from System A to System B. As noted in our sources, formally these are often called Application Programming Interfaces, or APIs, but the concept includes legacy methods like flat file transfers as well. In operations, we care deeply about these because they are common failure points. If the interface between sales and inventory fails, you sell products you don't have. We must understand that interfaces automate the transfer of data, removing human error but introducing technical risks. We will look at how these function, from internal connections within your data center to external links with vendors. This diagram illustrates the fundamental concept. Data flows from the source system into the interface layer. This is where the magic and the risk happens. The interface might transform the data format or route it. Finally, it lands in the destination system. Crucially, notice the dotted line to the monitoring system. Without monitoring the interface layer, you are flying blind. In IS operations, we generally categorize interfaces into two buckets: batch and real-time. Batch interfaces are like a bus schedule. Data waits until a specific time, say 2 a.m., to move in bulk. This is common for financial reconciliation or payroll. Real-time interfaces are like a taxi. The moment a user clicks buy, the data travels to the payment processor immediately. We also distinguish between file transfers, often used for batching large datasets, and API calls, used for immediate granular interactions. Understanding this distinction is vital because they fail differently. A batch job fails once a night. A real-time API fails thousands of times a minute. This sequence diagram contrasts the flows. In the real-time flow at the top, the user gets immediate feedback. The system processes the request instantly. In the batch flow below, the application stores the transaction locally first. Only later, at a scheduled time like 2 a.m., does it send a bulk file to the downstream system. This visualizes why a delay in batch processing might not be noticed until the next day. Often, systems don't speak the same language. Enter middleware. As described in the texts, middleware acts as the glue in complex environments. It sits in the middle, translating data formats, perhaps converting a PCS ASCII text to a mainframe's EBCDIC format. It also handles message queuing. If the destination server is rebooting, the middleware holds the message and delivers it when the server is back online. This ensures reliability. However, it introduces complexity. An operational failure in the middleware layer looks like a total system failure to the users. Furthermore, because it touches everything, it is a prime security target that must be hardened. Here we see middleware at the center of the action. The web app speaks modern JSON. The middleware accepts this, translates it for the mainframe, queues it for the database, and routes it to an external vendor. Without that central yellow node, the web app would need to know how to talk to 3 different, incompatible systems directly. Let's dive deep into APIs. An API is the exposed handle that other systems grab to interact with an application. In modern operations, APIs are everywhere. Your mobile banking app talks to the bank via APIs. Security here is non-negotiable. We cannot rely on simple logins. We use API keys and OAuth tokens to authorize every single request. A common operational risk is the shadow API, an endpoint created by developers that operations doesn't know about and therefore doesn't secure. As auditors, we must verify that all APIs are documented, authorized, and monitored for abuse, such as denial of service attacks via rate limiting. This diagram highlights the role of the API gateway. The client app doesn't talk directly to the backend service. It sends a request to the gateway. The gateway class shows its methods. It authenticates the token, applies rate limiting, and logs activity. Only then does it pass the authorized call to the backend. This encapsulation is the gold standard for secure API operations. Moving data is risky. Bits can flip, files can be truncated, and formats can break. Therefore, we need rigorous data integrity controls. We don't just trust that the file arrived, we prove it. We use checksums and hash totals mathematical fingerprints to verify that the file received is identical to the file sent. We also rely on record counts. If you sent 1,000 records and we received 999, the job failed. We also enforce atomicity. If an interface fails halfway through, we must roll back the changes so we don't have half a transaction in the database. Reconciliation reports should be run automatically to flag discrepancies immediately. This flow demonstrates the integrity check. The sender calculates a hash of the data and transmits both. The receiver calculates its own hash of the received data. The decision diamond asks, do the hashes match? If yes, the data is safe to process. If no, the data is corrupted. We reject it and alert operations. This simple mechanism prevents massive data corruption issues. A specific, highly structured type of interface is electronic data interchange, or EDI. This is how supply chains run. It involves B2B exchange of purchase orders and invoices. Unlike flexible APIs, EDI uses rigid, standardized formats like ANSI X12. Operations teams manage translation software that converts internal data into these standard formats. Key controls here include functional acknowledgements, essentially a digital receipt that says, I got your order and I can read it. We also use value-added networks, VANs, which act as secure post offices. Auditors must verify that manipulation controls prevent data from being altered before it is wrapped in the EDI envelope. The EDI flow is linear. Data leaves the internal ERP and hits the translator. It travels through the network VAN in a standard X12 format. The partner translates it back. Crucially, look at the dotted lines returning. These are the functional acknowledgements, 997s. Without that return loop, the sender has no legal proof the order was received. How do we trigger all these batch interfaces? We use job scheduling software. This is the heartbeat of operations. Schedulers manage dependencies, ensuring we don't try to process the payroll file before we've actually received it. A critical operational control is exception handling. If a job fails at 3 a.m., does the system retry automatically? Does it page the on-call engineer? Or does it just sit there? As auditors, we look for the audit trail of these jobs. We also enforce segregation of duties. The developer who wrote the interface script should not be the one scheduling it in the production environment. This Gantt chart visualizes dependencies. We start with extract data. We cannot start transfer file until the extract is done. We cannot load data until the transfer is done. Notice the critical red task. Verify checksum. This control step must happen after transfer, but before loading. If the checksum fails, the load data task must be blocked. We conclude with the auditor's perspective. How do we audit this? First, we ask for the documentation, data flow diagrams, and API specs. If they can't document it, they can't secure it. Next, we test the controls. Is the data encrypted in transit? We verify SSL/TLS certificates. We check the logs. Not just that they exist, but that someone reviews them. We look for fail secure states. If the interface breaks, does it fail open, unsafe, or fail closed, safe? We are looking for assurance that the digital handshakes between systems are firm, authenticated, and verified. This mind map summarizes your audit plan. The three main branches are security, integrity, and operations. Under security, check encryption and authentication. Under integrity, verify checksums and reconciliation. Under operations, review logs and schedules. Keep this mental map with you, and you will cover the essential bases of any interface audit.